All right, so we're looking at Unit 4 now. Pythagorean theorem, Pythagorean triples. And we'll get into square roots and quadratics and some cube roots. All right, so for now we're going to look at the Pythagorean theorem, some historical context here for you so you could read through that. The theorem itself, the sum of the square of the legs of a right triangle is equal to the square of the hypotenuse. All right, hypotenuse being the longest side, and that gives us a squared plus b squared equals c squared. All right. There are many different proofs of the Pythagorean theorem, but I'll just kind of walk you through this one. All right, just so you have a little bit of a kind of an understanding of how a proof would work in this context, but also it'll do what it intends to do, and that is prove that this is a valid technique. All right. So if I have, and I'm just going to kind of steal this diagram here. If I have a square, I'm just kind of move it off on the side here. That square is defined so that every side has a measure of c. All right, that was an intentional choice. All right, what we can do is encase this square inside of another square. All right, so we'll try to do that in one shot. Hopefully it'll work. There are some laws of geometry that are kind of at play here that I won't bore you with at this point, but it would guarantee that we end up with 4 congruent right triangles. Just trying to match this up somewhat nicely. I might have to move the square a smidge. That's probably the best I'm going to get. All right, so just darken this in. All right, so we'd have 4 congruent right triangles. I'm going to call the shorter leg, I'll call that A, and the longer one I'll call B. That gives me the length of this side as A plus B. Like I said, they're all congruent. So this line segment is congruent to this one, is congruent to this one, is congruent to this one. So they're all valued at B. And you could try this with real numbers if you want. Right? This other little line segment here is A, and they're all congruent to one another. And like I said, they're all right triangles, and that's because if I encase it in a square, all angles in a square are congruent, and they're all specifically right angles. So the length of this side here would be A plus B also. So I could find the area of the square. So area of the square, which is just going to be A plus B squared. All right. And just to be clear, when I talk about the square, I'm talking about the whole thing because I belatedly realized I probably should call it the big square, outer square. All right. So it's the area of the outer square, not the inner square. All right. So that's equal to A plus B squared. Now, if I distribute that out, a little bit of algebra here, a little FOIL method. A squared plus AB plus another AB plus B squared. Handwriting is has never been a strength, but in that case it was a little too much. So A squared plus 2 of those ABs plus B squared. Okay. Now, if I find the area of one of those triangles, That'd be 1/2 the base times the height. All right. Let me actually write out the word base because I've already used B to represent one of the sides. So 1/2 base times height. All right. Pick a triangle. It doesn't matter. They're all the same. We'll take this one. The base here would be B. So I'm looking for the area of that triangle. The base would be B. The height would be A. All right, so 1/2 AB. All right, but I do have 4 of those triangles. So I'm going to take 4 of those area of the triangles, which would be 4 times 1/2 AB, which is 2 AB. Now, if my ultimate goal is to find the area of the square, all right, I did it again, the inner square, all right, the area of the inner square is going to be equal to the area of the outer square minus the area of the 4 triangles. All right, the area of the outer squared is A squared plus 2AB plus B squared. The 4 triangles have an area of 2AB. The inner square itself, just going back to that, I'll just highlight that in yellow. I just need a thicker highlighter here. So this square here will have an area length times width, C times C, C squared. All right, so my inner square has a value of C squared. I have 2 opposites here, 2AB and a negative 2AB. So we end up with the relationship that C squared is equal to A squared plus B squared, which is the Pythagorean theorem. All right, so I could also write that as or A squared plus B squared is equal to C squared. All right, so that's one proof of the Pythagorean theorem. Most people, especially by the time you get to this course, will have used the Pythagorean theorem, but maybe you haven't really talked too much about where it's come from or where it has come from. All right, so the example here, when it says find the missing side, sorry, the formatting a little out of whack here, so let me just kind of move that over. That's something that was going to kind of bother me. It's not marked here, but we're going to assume that this is a right triangle. All right, that's an important thing to consider, at least up until this point. We wouldn't be able to find the length of the missing side using the Pythagorean theorem unless it was a right triangle, right? So something to keep in mind. But if I say that I have A squared plus B squared is equal to C squared, I'm going to designate one of my legs as A and the other as B, all right? So it doesn't matter which. This is going to be my C. My hypotenuse is always the longest side. I tend to go smaller side as A, and the larger leg would be the B. All right, so I'd make those substitutions and use that to solve. So I would have, well, I almost wrote the wrong thing there, 9 squared plus 40 squared is equal to C squared. All right, so that's 81 plus 1600 is equal to C squared, so 1681. And then we could take the square root, right? So you could also do it all in one shot if you want. 9 squared plus 40 squared gives you the 1681, and then the square root of that, and you you get the 41. Right? So 41 is equal to C. And again, we get that by taking the square root. Something to keep in mind, I'll show it here just the one time. When we talk about quadratics, it'll matter more. But for now, since we're talking about geometric context, we wouldn't consider negatives to be an issue. But technically, or at least by the math of it, if I take the square root of C squared, so left-hand side, square root of 1681 is 41. The right-hand side, that's equal to the absolute value of C, which means that C could be positive or negative. So 41 would be equal to C, or a little V symbol for or. 41 could be equal to negative C, which means that C could be equal to 41 or negative 41. Another way of writing that would be C is equal to plus or minus, positive or negative 41, right? But in this context, we toss the negative because we're talking about the length of a side. The only time negative, or not the only time, but the most common time for negatives to become relevant in a geometric context would be if you're talking about not just a distance, but also a direction. So instead of saying 41 inches, I'd say 41 inches to the left versus 41 inches to the right. So it gives us a sense of direction, right? But that's just a little aside, and we'll talk about that more when we get to quadratics, just to kind of get across a particular attribute of that. It basically boils down to there are some instances where we do care about a negative result of a square root as opposed to a positive, and so I'll talk to you more about that when the time comes. So that was a pretty straightforward example. Same idea here. This time we're solving for one of the legs, right? So this is my C. I'll call this one the A. I don't know necessarily that it's the smallest side, but it doesn't really matter because it's commutative. So A squared plus B squared is equal to C squared. X squared plus 13 squared is equal to 20 squared. Now, that's what I mean. If I were to write x squared plus 13 squared or 13 squared plus x squared, I would still end up with the same value of x after doing my algebra. So it ends up not mattering because addition is commutative. You can add in either order and still get the same result. Right, so x squared plus 169 is equal to 400. My equal sign elevated itself for some reason. I'm going to subtract off, just going back to what we talked about with solving linear equations, whether you're using an inversion approach or modern algebra. X squared is going to be, that's going to be 231, I think. Let me just double check. Yeah, 231. I'll take the square root of 231, and I get this decimal value. So we would say, again, applying the square root, disregarding a negative, I could say x is equal to the square root of 231, or I could put the decimal equivalent, depending on what the directions ask, in this case 15.2. I always try to be mindful of the practical application of this. So if I were trying to figure out how long to cut a piece of wood, right, so if I was like, all right, so I need to brace this door, I was just thinking about some of the security devices that you might have for like your front door. It kind of leans against the doorknob and against the floor. It creates a little angle with the floor. So I'll just draw a little diagram so you don't have to guess what I'm talking about here. So here's the door. Here's the floor. I was waiting for that to snap in. And then here's the doorknob. And it'll have like a little kind of a hook here. And then a little rubber stopper here so that the door won't open. Well, I mean, I guess nothing is perfect. I mean, it won't easily open, we'll put it that way, not without causing a ruckus. But if I needed to know what this distance was, like how long of a device should I buy, assuming that it's not the kind that extends, things like that. There's a lot of assumptions that need to be made. I could use the Pythagorean theorem. I know how far off the floor this would be. I know how much room I have available here. I could use the Pythagorean theorem to find that missing side. Right? It's just a simple calculation that I'm sure nobody would ever do. You just buy it on Amazon. Doesn't fit? Okay, free shipping, return it. Right? But, if you wanted to try to apply some of this stuff, you could do that calculation. But if I use the Pythagorean theorem, or if I ask somebody else to do it for me, and I said, okay, how long of a pole should I buy? And they told me, let's get a pole that is the square root of 231 inches. You'd be like, all right, thank you. That's so very helpful. What would that actually be? You'd say about 15.2, so about 15 inches. Now that would be pretty small based off the example that I'm giving. That's not even a foot and a half, but that's the idea. Like I would want to know the decimal value or ballpark estimate. If I said that I have a distance that needs to be traveled of 20 inches, how far up the wall would I have to go, or how far out could I go? And I'm just looking for a ballpark estimate. Radical 231 wouldn't really fit in that context. So in real life, we tend to sacrifice a little bit of accuracy because in many cases an estimate works. That's why things like if you're familiar with any kind of carpentry or anything like that, like a shim, if you've ever heard of a shim, that then you're kind of seeing that a little bit of accuracy is sacrificed in order for efficiency, right? And the ability to not have to solve an equation every time you want to build something. You could also do word problems. Some of them are more geometric, I'll say academic, than practical. Find the diagonal of a rectangle with a length of 24 and a width of 10. Right, so that would be the hypotenuse of this triangle. All right. Let me thin that out actually a little bit. Oops. All right. It's a rectangle, and all the angles in a rectangle are right angles. All right. So I would say a squared plus b squared is equal to c squared. 10 squared plus 24 squared is equal to my unknown. All right, so that's 100 plus, is that 576? 476. 576 is equal to c squared. Oh, I could have looked at the bottom of the screen. Plus 100. Oops. Answer plus 100. So I would take the square root of that, and I get an even 26. All right, so C is equal to 26. All right, so that's one type of word problem. Another is the attempt to be more practical, I guess. In a pond, a flower. It doesn't always play out, though. The flower of a water lily is 4 cubits, which is an ancient unit of measurement, above the water. All right. When it is bent by a gentle breeze, it touches the water at a distance of 8 cubits. Tell the depth of the water, and this is a Chinese problem, right? So ancient Chinese question, academic. So we want to know the depth of the water. So we define that as a variable. The total length of the water lily plant would then be x plus 4. All right. So the rationale behind that is this is obviously not a realistic looking diagram, but so we have this plant that's rooted somehow under the water and grows to reach its total height at some point above the water. All right. Then what happens is the wind blows Let's see if I could do it this way. The wind blows and pushes the water lily onto its side. It's still resting on the surface of the water, all right, but it's sweeping through that distance, all right. So it's got a movement. I don't think I can move it and relocate it, but the wind is blowing it down on this axis, right, and it's ending up in this position, right. So whatever the depth of the water is, because it's rooted in the base of the water, the riverbed, I guess, and then growing to a certain height above the water, that it would be the total length of it, right? So what's happening here is once it moves into that new position, it's still going to have the same height that it had originally, right? The depth of the water plus whatever it extended to above the water. So that gives me two legs of a triangle, X and 8. Right, so this is my X and this is my 8, as well as the hypotenuse. So using my Pythagorean theorem, a squared plus b squared is equal to c squared, x squared plus 8 squared is equal to x plus 4 squared. They're asking us to figure out the depth of the water, right? And so that would be whatever the value of x is. All right, so on the right-hand side, I get x plus 4. I multiply that by itself. All right, a little distributive property. X squared plus 4x plus another 4x plus 16. On the left-hand side, x squared plus 64. All right. These two like terms could be combined. X squared plus 8x plus 16 is equal to x squared plus 64. Using my algebra skills, I can subtract an x squared from both sides. It happens to cancel on both sides, which is nice, because that was the most complicated part of it. I'll be left with 8x plus 16, subtract off the 16. I'm looking at 48 equals 8x, divide out the 8, and I get 6 equal to x, so it would be 6 cubits. All right, so there's kind of a lot going on there. You could apply the perfect square formula if you want, but really just distributing out is probably the easiest way to handle it. All right, so yeah, that's the approach I would use, but you can see the solution here also. All right, so the remaining problems are all kind of on the same line, along the same lines. Or I pluralized the words in reverse. The remaining problem is along the same lines, right? So you can try this problem, and then in the next video I'm going to move on to Pythagorean triples, and then we'll have a little practice set related to this.